All right, looks like they're finally done with their announcements. That took a while longer than I thought it would. But so today we're going to be covering De Morgan's laws. We've been talking a lot about Boolean statements up to this point, and this starts falling into that. This is a little bit more, I'd say, nuanced. One second, it just popped up with like a error for me. I don't know what. Next. Oh, yeah, it says it's lower than what is recommended. I don't care. All right. Okay, so we're gonna get into this. If I don't think anyone's on, but if you are watching this, there will be points probably where I pause. If I have viewers, I'll probably actually pause. But until I see that I don't, I'll just kind of run through things. Hopefully, you're pausing at places like the warm up, so you can actually do that type of stuff. All right, so warm up for today. Create a concept map by brainstorming any concept ideas and any concepts and ideas. There we go, of ideas that come to mind. So this example here, this is a concept map of where we have what is a tree. A tree is made of roots. A tree is a bunch of trees, like plural if you do. A tree has leaves. A tree can provide shade. A tree can be how we make paper. We make books out of paper and notepads out of paper, and so they're kind of a little bit related. So what can you think of with a tree? Then you can add arrows, kind of just like this. If we had trees, we go to paper, we go to books, all that type of stuff. Kind of like what's the process of how is everything connected to each other? And just kind of like I did, use to make books, all that type of stuff. Oh, oh, there it is. I knew I had it somewhere. How is logic incorporated in a program? So kind of pause, take a minute, and think about how is logic incorporated in a program, and design that concept map. I don't think I had any viewers, so you'll pause at this point and you will complete this concept map. All right, you probably can't share with the neighbor because you are not at school today. So we'll keep moving on. So today, your lesson objectives. By the end of the lesson, you're going to be able to evaluate compound Boolean expressions for equivalence and use truth tables to prove De Morgan's laws. Yeah, I know you thought proofs were gone whenever you left geometry. However, we can still prove certain elements of these laws. So your question of the day, and your question you're probably asking right now, is what are De Morgan's laws? So we worked on this last class. This is the kind of truth tables that we started to evaluate. And in this we have A, B, obviously that's not too new for us. This is the not symbol. This is a set of parentheses. A, this is the and evaluation. B. And as we know, the parentheses happen first and then the not happens, and so we can actually test this. So if I have A is true and B is true, I look in my kind of statement here, I say true and true, so this should be true. This not does the opposite, so it should be false. All right, next one I have true and false. So an and statement requires both of them to be true in order to return a true value, so this is going to return false. Hopefully you can see like that. Yep. And then it has a not statement, and so that's going to be true. It's the opposite. It's going to return the opposite. It's yes, no. False, true. They're not both true, but we're doing the opposite, so it's going to be true. False, false. Neither of them is true, which is required for an and statement, so we're going to get, but we're doing the opposite of that, so it's going to be true. This one, A, B, we have not A or not B. And what we're looking for is we're looking for a true statement. And so the opposite of this is false. The opposite of this one is false. They're both false, so it should be false. This one's true. This one's false. This one gets changed to a false. This one gets changed to a true. So one of them is a true. Same thing with this line. False, false. They're both false. However, we're doing the opposite, so we get a true. All right. Okay. All right. So you can't really discuss with your partner. However, if you were working on this with a friend, you can use a truth table to help determine if two Boolean expressions are equivalent. How could you check if they're equivalent? And actually, I can even go back here and kind of start saying, looking at that type of thing. All right. So, what are De Morgan's laws? De Morgan laws are a set of rules that describe how to simplify complex expressions. And really what this is talking about is this is a way of how do I make this more compact? How do I make it so that it's not like you can make this really, really, really complex, and we want to make it kind of less complex. So, kind of the ways to go about this is move the not inside, and becomes or becomes and that's a very general idea of it. We're going to get into kind of more of the detail of what that means here in a second. So, with De Morgan's laws, the first thing is move the not inside, and becomes or becomes and. So what we do is we move the not inside. So we have not a. We move the not to the and sign. And so what that means is the and, whenever we kind of choose, like we do the opposite of and, we make it or. So the opposite of and is or, and the opposite of or is and, kind of more or less general statement. So if we do that, we also then do, because we just did not a, not and, so which makes it or, and then not b. If it's not a or not b, we're going to have the answer. If we did this with an or statement, if it's not a, if it's not a, we move this not to the or statement, and that's going to make it and. And then we're going to do to the b statement, and b. And what this allows is this allows you to do that short circuit evaluation that we were talking about earlier. That short circuit evaluation is a way of being able to kind of quickly look at something and evaluate it really quick, instead of kind of going through that whole process I was doing a little bit ago, where we are doing A or B and then doing the opposite. We're able to evaluate it a lot faster by just being able to look at this kind of more simplified expression. So, two Boolean expressions are considered equivalent if all of the final resulting truth values are the same. So if I look at this, I have this not A and B, and this is inside parentheses. If I move it like we did just a little bit ago, it turns into not A or not B. And whenever we do that, we get false, true, true, true. Over here, we get false, true, true, true. So these are the same. And that's what we want. We want them to be the exact same. Okay. All right, that works for what we were just talking about, works for just kind of like our typical Boolean like and or statements. But now we start saying, hey, but what about adding in different signs? What if we have a sign of some sort that says, hey, this is how we're going to change things. Or sorry, not change things. How we're going to kind of equate these two things. It's not always and symbols, it's not always or symbols, or maybe we're doing a combination of these. We can use De Morgan's laws in order to provide, even for equivalency, I'm just going to go with equivalency type situations. So if I have not a, I guess the way to read this kind of really is, does A equal B do the opposite, right? That's kind of the way that we think about this is, does A equals B do the opposite? So what we got here is we can say, we can take this and we can actually do the same thing. And what we do is we flip the sign. In this case, don't really have much of a way. But the way that we flip the sign is we make it not equal to B. If A is not equal to B. If we did the opposite of that, it would make it so that it equals B. And this can be one spot that's a little confusing, because if we look back here, whenever we did this evaluation, we did it to the A and to the B, and we also did it to the or. We did it to all three of them. And that's, whenever we're talking about equivalencies, this is kind of This is the true false. Like this section, let's see here, I can turn this on. This section right here is the true false. We need this to equivalent to be true false because this could be like 2 and this could be 4, right? And it just wouldn't work. We're not getting a true value here and a false value here. So we're looking specifically for those booleans. All right. Okay. Oops, I thought I clicked the eraser. Erase all. Okay, cool. With this one actually is probably a little bit easier for you to recognize of what it would probably become. Hopefully you can guess. You probably tried just flipping this sign. And yes, we did do that, but we also added an equals to sign in here. And the reason for that is if this number was 3, we're saying, is it less than the number 3? The opposite of that is, so all of our valid possible answers are 1 and 2, and I'm just going to say whole numbers. If we did the opposite of that, and remember this has that not statement in here, anything that's greater than or equal to 3 is also a true value in here. Okay. All right. If we do this one, and you probably guess now because you've seen this previous one, that what we're going to do is if it's less than or equal to b. Again, this has to deal with what numbers are valid for this result, because we have to pay attention to that not. That not is just kind of what's throwing the loop in everything and kind of making things a little bit more difficult. And so we're trying to simplify that not statement. All right. So the next one we got is if it's A, if it's less than or equal to B, make a guess. I think you're going to get the right one. Notice that we're dropping that equal sign because the equals is a potential answer. Make a guess on this one. That's right. It should be A is less than B because we're dropping the equal sign and we're flipping the sign. All right. I will put the link to this specific, actually I wonder if I can just do it on, no, I can't. I'll put a activity guide so that you can work through this activity. You can print it out. You can do it by digitally if you want. Go through and work through this truth table. Yeah, we'll figure out how to make this happen. Maybe this is something that we do whenever we get back to school. Right. Okay. So, 2 software engineers have written these code segments to solve the same problem. This is very common in computer science where you're going to have 2 different approaches to the same thing. You can have one programmer who thinks one way and a different programmer who thinks in a different way. So go ahead and see if you can figure out which one of these kind of might be a little better. Simplify them and see if they are equivalent. It's a good way to check for stuff. And so, yeah, hopefully that's helpful. Actually, I guess, yeah, go ahead and pause here if you are working on it. Make sure you can get this before you go and check the answer. Things I'll point out is that this is one whole true check. This is one whole true check. This does have an and symbol in it and a not on the outside. Okay. All right, so let's see what this turns into. So what we're going to do is we're going to be flipping the sign and changing things. So Sarah get x not equal to 3 turns into Sarah get x equals 3 because we're changing this sign. Again, this is one of the truths that we're checking. Sarah get y not equal to 5. We're evaluating this and we get, hey, it's equal 5. This is one of the truths that we're checking. We then, need to also change the and sign to be or. So this turns into or. So we get Sarah.get x equals 3. This is from number 2. Yes, or Sarah.get y equals 5. Yep, those are the same. So today you have learned about evaluating compound Boolean expressions for equivalence using truth tables to prove De Morgan's laws, and answered the question of the day of what are De Morgan's laws. Here's your vocabulary. If you need this, you can definitely pause. Otherwise, that